to solve another Leetcode problem, 407, trapping rainwater 2. So for this problem, we are giving m times an integer matrix. It is called heat map, representing the height of each unit cell in a 2D elevation map. So we're going to return the volume of water it can trap after raining. So inside the drawing, we can see something like, so this is the map. And because after the raining, maybe somewhere is lower and it can trap water. So in this area, so it's gonna be the water. Yeah. So for this example, the answer gonna be 4, and in this example, the answer gonna be 10. But exactly how can we solve the problem? It's gonna be really difficult to think about. But actually, the coding gonna be a little bit easier if we understand how to solve it. So let me make a 2D drawing, because 2D is going to be easier. Instead of making a 3D drawing, it's difficult to draw. But let me just make a 2D drawing. So this is our layer. This is the outside layer. So for example, it's going to be a rectangle. So this is just the outside layer. Maybe we're going to have some values. Yeah. So let me represent the height. Yeah, and so for all those numbers, so the drawing will be like this. So for all those numbers at the outer side, I mean at the last layer, we're gonna check what is gonna be the lowest height. So maybe, for example, this is 1, and all other areas are gonna be 2. So what's going to happen for this kind of situation? So this means just inside. If it is 0, definitely we can trap water. And here is also 2. Yeah. So definitely we can trap water because this is 1 and other areas is 2. So the lowest area is 1. And this area is 0. So this means we can trap 4 units of water, because this is 0, 0, 0, 0. Yeah. But what if this is 2? So this means we can trap 4 times 2, 8 units of water. So how much water we can trap? It is always dependent on which height at the outer side is the lowest. So if the lowest is 1 inside our example, so we're gonna check this 1 as the lowest area. So then what we're gonna do? We're gonna use this one to minus the height of this one because it is its neighbors. Yeah. So first of all, we're gonna put all those values at the outer side to a priority queue. It's gonna be a min heap. And inside of the min heap, definitely we can find the minimum value, which is gonna be this one. So the min heap, we can find the minimum value, which is gonna be 1. And then we're gonna use BFS to check the next layer. So the next layer is gonna be 0, 0, 0, 0. So by using the min height minus the 0, so 1 minus 0 times 4, so we can collect 4 units of water. And we're going to continue to do such kind of things. So after using the outer layer, we cannot use the outer layer anymore. So we're going to reset the outer layer to be -1 or -infinity. It is okay. We just need to check. We will not go back for the BFS. We just need to check. So it's going to be something like this. So this is a circle, and we find, oh, this is the min height. Maybe this is 4, and other areas maybe 5 or 6. And then we're going to check the next layer. And then we're going to check the next layer until we find all of the layers. Yeah. So the idea is that this is 4 for the next layer. Maybe here, this is the neighbor of its next layer. Maybe this is 5. Yeah. So after this next layer, maybe the min height is not 4 anymore. It's going to be 5 because other areas may be 6, 7, 8. But this 5 going to replace the 4. Yeah, because if we take out this 4, it doesn't mean the min height is 4. It is not 4 anymore. It's going to use this min height. Maybe it is 5. Yeah. So this is the basic idea. So if we understand like that, basically we can start coding. So how much water we can collect? It always calculated layer by layer. First, the outer layer. If the outer layer is it can never collect any water because it is the outer layer. But after the outer layer, we find the min height, and then we can collect the water for its neighbors. And then to its neighbors, we can always collect water. We just need to calculate how much water we can collect. And in this way, the time complexity is going to be mn times log mn. That is why it works, because m times n is going to be 10 to the power 5. Let's just check. It is not 10 to the power 5, but mn is going to be 200 times 200. It's going to be 40,000. It's going to be a small number. That is why it works. Yeah. So now let's just start coding. Actually, coding is much easier if we understand how to solve the problem by using BFS with a priority queue. So I'm going to prepare row and column. R and C is going to be length of the heat map and the length of the heat map 0. And I'm going to prepare a priority queue. It's going to be empty. Then I'm going to loop through it. So for R row, enumerate the heat map. For C is for column. So for C heat, enumerate the row. If R equal to 0, yeah, I just need to check the border, or R equal to R minus 1, or C equal to 0, or C equal to C minus 1. This means I find its border. So now what I'm gonna do, I just need to put it inside the priority queue. So pq.append. First of all, I'm gonna append the height, because I'm gonna calculate the mean height. The height, the row, and column. I think that's everything about it. Yeah, but after I put it inside the priority queue, I need to use a weighted set. So here I'm gonna directly use the value. So the heat map with the row and column, I'm gonna set it to negative infinity. So basically this means all the outer layer has already been weighted. I will not weight it anymore. Yeah. So this is the first step. After that, I'm gonna use a heapify to heapify the priority queue. Yeah. Now we prepared a priority queue. After that, we just need to check the priority queue. So while pq, we're gonna check the mean height. So this is gonna be the mean height. This is gonna be row and column. It's gonna be the heap pop for this priority queue. I'm gonna prepare a direction because it's gonna have 4 directions. So inside it's going to be 0, 1, 0, negative 1, and then it's going to be 1, 0, and negative 1, 0. So this is going to be the 4 directions. I just need to check 4 directions. So for drdc, inside the directions, I'm going to update the new row and column. It's going to be r plus dr and c plus dc. Now I just need to check if it is inside the boundary or not. So for this new row, if it is inside the boundary, and for this column, if it is inside the boundary. And I also need to check this is not visited. So this means for the heat map with this row and column should be more than or equal to 0. Yeah, if it is like that, basically I want to. Yeah, if it is like that, basically I want to put something inside the priority queue. But I can also check the final answer, how much water I can collect. So I'm gonna set a variable result to be 0. Yeah. Now I want to check how much water I can collect. So the result is gonna plus equal to what? It's gonna be the maximum, because I'm gonna check the maximum value of this mean height and minus the heat map of this row and column. So this is how much water I can collect. But it can be a negative value, so I'm going to use a max with a 0. Because if I cannot collect anything, I'm going to collect 0 water. Yeah. Now, I want to put something inside the priority queue, so I'm going to use a heap boost. And inside, it's going to be this new heat map. Yeah, it's going to be this heat map and this row and column, right? But this heat map, we should consider it compared with the mean height. because we're gonna choose the maximum value, otherwise it didn't work. It's gonna be the maximum value of the min height. Yeah, because if this heat map is lower, it is okay, but if my min height is higher, I'm gonna choose the min height. Otherwise, if this heat map is higher, I'm gonna choose the heat map with this row and column. Yeah. I think that's basically everything about it. But as this row and column has been visited, so I'm gonna set it as visited. So heat map with a row and a column, and to be a negative value. Yeah, because from here I'm gonna tag if it is more than or equal to 0, this means it is not visited. If it is visited, it's gonna be a negative value, so it's gonna be less than 0. So this means I'm gonna tag layer by layer until to the inside. Finally, I just need to return the final result. Yeah, I think basically that's everything about it. Now let me just run it to check if it works. Now as you can see, it works, and let me just submit it to check if it can pass. Yeah, now as you can see, it passed for all testing cases, and it's pretty fast because the time complexity is just m times n times log mn. Yeah. Why? Because here we use a heapify. So for here, the time complexity, row and column, yeah, is m times n. But for here we use the BFS. So for each one, it's gonna be log n, and how many nodes we used, it is m times n. So the time complexity gonna be this one, m times n times the log mn. Yeah. I think that's all about it. It is a little bit difficult to understand, but actually the coding is gonna be much easier. So let me just try to explain once again about why we're gonna write it like this. I think the difficult part may be about this one, the maximum of the min height with the heat map row and column. Yeah, so let me just make a drawing to explain why we're gonna do it like this. Yeah, so something is gonna happen like this. So this is our outer layer. So this is the min height. This is 4, and other areas maybe 5, 6. It doesn't matter. Maybe 6, 7, or maybe 5. Maybe here is 5, here is 5, but here is 4. Yeah. So we're gonna put this. This is min height, and we've already put it inside the priority queue. And then we're gonna check its neighbors at the left and the right side. We don't need to check because we've already put it inside the priority queue, and we already set it to a negative infinity. This means it has already been visited. But at the bottom side and the top side, there's nothing because this is the border. But at the bottom side, if there's a height, and this height is 5. So now, what gonna be the min height for this area? It's gonna be 5, because 5 is bigger than 4. So this min height is gonna be 5, because maybe other areas may be 6 or 7 or something, but it's gonna be 5 instead of 4 because I have a higher border. So definitely I need to choose a higher border. Yeah. But if it is not 5, if it is 3, it is okay because this border is higher. Definitely, if the water areas is equal to 4, definitely I can still hold the water because this is 4, this is higher. Even the water is gonna drop out, but it's gonna hold at these areas. This is why we're gonna use this kind of a max check. I think this is the only difficult part. If you understand this one, definitely we can solve the problem. Yeah. I think that's all about it. Thanks for watching. See you next time.